أعوذ بالله من الشيطان الرجيم. بسم الله الرحمن الرحيم. وإذا مس الإنسان ضر دعا ربه منيبا إليه ثم إذا خوله نعمة منه نسي ما كان يدعو إليه من قبل وجعل لله أندادا ليضل عن سبيله. قل تمتع بكفرك قليلا إنك من أصحاب النار. أمن هو قانت آناء الليل ساجدا وقائما يحذر الآخرة ويرجو رحمة ربه. قل هل يستوي الذين يعلمون والذين لا يعلمون؟ قل هل يستوي الذين يعلمون والذين لا يعلمون؟ إنما يتذكر أولو الألباب. قل يا عبادي الذين آمنوا اتقوا ربكم للذين أحسنوا في هذه الدنيا حسنة وأرض الله واسعة إنما يوفى الصابرون أجرهم بغير حساب.
Good morning, everyone and all. It's a privilege and an honor to extend to you all a very warm welcome to the official inauguration of our first National Symposium on Visionary Excellence in Engineering, VEETA 2025. We are gathered here today to engage in celebration of knowledge, innovation, and academic collaboration, a testament to the collective pursuit of excellence in the field of engineering. We are especially grateful for the presence of the chief guest, Dr. Hamdan Al-Fazari, Vice Chancellor, Sohar University, and our dignitaries and participants whose participation add prestige to this event. To formally commence the proceedings, I now have the honor of inviting Mr. Hood Asadi, Head of the Engineering Department, to deliver the inaugural welcome address and share his insights on the significance of this gathering, as well as to address the audience and set the tone for today's symposium. Welcome, Dr. Hood.
Assalamu alaikum. Good morning. Dr. Hamdan Al-Fazari, Vice Chancellor of Sohar University, distinguished guests, respected colleagues, students, and esteemed participants. It is a great honor and privilege to welcome you all to the National Symposium in Visionary Excellence in Engineering, Technology, and Applied Sciences, VEETA 2025, proudly hosted by the University of Technology and Applied Sciences, Chinas. VEETA 2025 serves as a dynamic platform for presenting groundbreaking research and foster insightful discussion across a wide spectrum of specialization, including robotics, artificial intelligence, the Internet of Things, renewable energy, environmental sustainability, material science, and other emerging fields that are shaping the future of engineering and applied sciences. We are pleased to share that VETA 2025 received over 100 abstract submissions and 29 posters. From this, 31 high-quality research papers from researchers and 32 outstanding contributions from the students have been accepted for presentation. We are also honored by the participation of more than 12 national higher education institutions, alongside over 9 international institutions joining us virtually. In addition to the academic session, we are delighted to host an exhibition that showcases real-world application and innovation, reflecting the practical impact of engineering advancement on society and industry. I would like to take this opportunity to express our heartfelt gratitude to Sahara Aluminium for their support. A special note of thanks to our esteemed keynote speaker and to all our engaged participants for their valuable contribution. Our sincere appreciation also goes to the higher management of UTAS SINAS, the supporting departments, and everyone who worked behind the scenes ensured the success of VETA 2025. Finally, I extend my deep appreciation to the engineering staff and all contributors whose hard work, delegate, and collaboration made this symposium a resounding success. Welcome once again to VETA 2025, and let's the journey of visionary excellence begin. Thank you.
With the formal opening complete, we proceed to the highlight of today's program, the keynote sessions, where esteemed speakers will share their expertise on current trends, challenges, and future directions in engineering. We begin with the first keynote speech. Dr. Muhammad Al-Abri, our Director of Nanotechnology Research Center at Sultan Qaboos University, to give his take on advancing renewable energy through nanomaterials and catalytic innovations. Please join me in welcoming Dr. Muhammad Al-Abri.
السلام عليكم ورحمة الله وبركاته. بسم الله الرحمن الرحيم والصلاة والسلام على سيدنا محمد وعلى آله وصحبه أجمعين. It's a privilege and an honor to be standing in here in front of all of you talking a little bit about the Nanotechnology Research Center. As you see, my name is Muhammad Al-Abri. I'm a professor of chemical engineering in the Department of Petroleum and Chemical Engineering. I'm also the director of Nanotechnology Research Center. And today I'm going to talk a little bit about part of the work that we do in the Nano Center in renewable energy, mainly. Not all the work that we do in renewables, but brief talk about hydrogen, green hydrogen production, a little bit of CO2 fixation as well. So I'll try, they say, give the mic to somebody from the industry, they will finish in 5 minutes. Give it to an academic, they will take an hour. This presentation is basically, I think, 40 minutes, and I have 20 minutes, so I will skip all of the scientific part, inshallah ta'ala. So we began in 2011 as a nano chair. 2015, we had an extension, so it was 100% funded by the Research Council, now the Ministry of Higher Education. In 2016, we basically moved to be a full-fledged center in nanotechnology, and since then we have been working as a center in nanotechnology applications. One of the things that we are very strong with is our nano labs. We have 2 labs, big labs, with state-of-art equipment. Actually, we began with a funding of 2.9 million Riyal Omanis as part of the chair. Until now, so far, I think we had a budget of around 6 million for our research in the center. And that's why we are very, very fond and, of course, very proud of our equipment that we have in the lab, well, it's in water or whether it's in material characterization. And because of that, we also had a lot of work on capacity building. We had more than 70 RAs, research assistants, trainees. So far, I think we had here 13 PhD students, 17 master students, supervising or co-supervising with different, it's not only in SQU, but also in different countries all over the world. We currently have 2 PhD students or 3 PhD students in the UK, 1 PhD student in Malaysia, and 5 PhD students in Sultan Qaboos University. As well as so far since 2017 we have 7 or 6 patent applications. One of them is this. Basically, when we began as a chair, we began in water treatment and desalination. When we founded the center, we moved also to other fields. And what we've done is we looked at what kind of technologies we have. We have the capacitive deionization part, which I will probably talk about in the next slide, and we also have the membrane side. We began with the fabrication, very basic, very simple fabrication of membranes for water treatment and desalination. And once we knew how these are done and we got the capacity in our lab, we began with experimenting in how to make these membranes better. We've done carbon nanotubes. The commercial carbon nanotubes are not good with membranes because of the hydrophobicity, hydrophilicity thing. And so we had to do our own carbon nanotubes in the lab. So we fabricated, and we have a patent on that, specifically carbon nanotubes suitable for membrane fabrication. Then we looked at that technology and we moved it into the medical field. So that was our second patent on application of nanomaterials on the fabrication of membranes for medical applications. From there, we tested a new technology for more enhanced, more efficient membranes, cheaper to make, dual layered membranes. After that, we looked at membrane recycling because all of our water that we have is from desalination, right? And desalination relies on reverse osmosis. Now, after the end of life of these membranes, they are discarded. What we have done is we took these membranes, we recycled them, we treated them, and we can return them back to for other uses. Of course, not for desalination, but for water treatment, it's possible. But then again, we moved to other areas. So we have another patent for green hydrogen production, and I'll briefly talk about it. And we have a patent on nanosensors as well. So as I said, when we began where the center is, or the chair was in desalination, specifically desalination. But now we are dealing with the application of nanotechnology in water treatment desalination, in the oil and gas industry, in renewables, and in industrial applications. And part of the work is something like this. We've done nanosensors, but these nanosensors are actually different. So it's not even the same technology. We have nanosensors from the water aspect, and so biofouling. And this is basically a little bit different than the nanosensors for hydrogen detection, CO2 detection. So these are 2 different fields from 2 different teams working separately, but also discussing from time to time to see how we can manage to combine both of them. But the technologies used are also different. We have CO2 fixation. We have around 6 projects on CO2 conversion to added value products. I talked about green hydrogen production. We have membrane distillation. The thing is, this membrane distillation goes very well with the capacitive deionization. When we began with capacitive deionization, this is a new technology desalination process specifically for the desalination of brackish water, salty groundwater. And we know that this is a huge problem for us in Oman, especially in Al-Batina, both governance, and also it's a problem in Dhafar, and we can see the effects also even in Dakhiliya. So the capacitive deionization, it's not good for seawater desalination at all. However, for low salinity, it's very strong. We began with that, we worked very hard, we think we got 4 patents on it. Unfortunately, the core team that was working on it left, and now they are one of the most innovative companies in the EU. They are located in Sweden, specifically for CDI. Now, the membrane distillation is completely different. It is specifically used for very highly saline water. Again, seawater is not good. It's for salinity of at least double or 3 times the salinity of seawater. We have a pilot plant with the Ministry of Agriculture, and what we used it for, because in the desalination of inland farms, the brine coming out that is not used is returned back either as flooded, or it's returned, of course, in Al-Batin, they don't return it back to the well. What we do is we will use this membrane distillation so that we have another step of desalination. It's very good. It's unfortunately with this, the problem with it is the energy consumption, and so we are working on reducing the energy consumption using renewable energy. When we talk about renewable energy, green hydrogen is not really energy, it's an energy carrier. We have done a lot of work on solar cells. We've done solar cells, dye-sensitized solar cells. We have done perovskite solar cells. We've got hybrid. Unfortunately, we don't have the industry on building these from scratch. So after that, we moved into green hydrogen and CO2 fixation. So why the interest in green hydrogen? Of course, we know that Oman is highly interested in green hydrogen. And what we are, as an academics, as researchers, we are supportive of the community that we have. Now, if you look at the plan, and this is the Oman's plan, so our interest is not really to produce and then sell whatever. We are not an industry. What we are researchers. We are looking at the numbers and see where we can contribute in the community. And if you look at the plan, the plan is between 1 and 1.3 million cubic tons by 2030. That is a requirement of 8 to 10 gigawatts of electricity. Only for the electrolyzer, we actually need more. And if you look at that number, we are currently, in Oman, using 14 gigawatt per year, producing in Oman. So this is practically around 75% only for the green hydrogen. Only for producing green hydrogen in 2030, we will require around 70% of the current power demand. That's a huge amount. And it gets even higher. It's 3.25 to 3.75. This is basically, if you look at this is around 15% of the current demand worldwide. So the current demand for green water is something like that, and Oman is planning to produce the same amount that is demanded now. Of course, in 2050, it's just very huge number. And of course, if we want to do something like that, we need a lot of innovation. Now, if we look at the hydrogen production plant, what they say is currently green hydrogen cannot compete with any kind of other hydrogen color, whether it's blue, brown, or gray, whatever it is, because it's extremely expensive. What they believe are, of course, not me, I'm not in that area. They believe that there will be a huge cut in the production and utilization of the electrolyzer by 2030. That is because the current technology that we have, we are using these electrolyzers, they are extremely expensive. Now, 55% is on the balance, and if you look at the balance, 50% is only the power supply. The power supply for green hydrogen production. But on the other side, 45% for the electrolyzers itself, you will see that almost all of that goes into the bipolar plate and the coated membrane. And if we look at this, it's because you can see that on one side we have the iridium, the other side is platinum, and we have gold as well. These are extremely expensive, using them in these plates, polar plates or on the membranes. And the plan is what they think is, and what we think is possible, is moving from these expensive metals into using earth abundant metals like copper and nickel. So if we can move to this transition from these expensive elements to more readily available cheap elements, then probably we will definitely see a huge drop in the cost of producing green hydrogen compared to the others. And that's why we have worked on this. Now, we began with green hydrogen in 2022, probably the first work that we have done. Before that, we were working on the other kind of renewables and oil production. So whatever I'm going to present now, it began in 2022. So the first part is, of course, trying to see how much can we get to the current commercial part. And as you can see, I don't have a pointer over here. This is the starting point. We are good, but we are still not within the commercial side. And that's understandable, because we just began. We are not there yet. We are still building actually the lab. We were buying the equipment and training our students, training our staff. But we had very good results, as you can see from A. We are still within a good thing, but it's not that good. The numbers over here is 161, 167. We need lower than that, much lower than that. So we continued with that work. This is a different one with the SEM and looking at the structure of the catalyst itself. What we do is we put the catalyst and then we dope the catalyst on the electrolyzer, or the electrodes, so that we increase the surface area. We have a better surface area for the work. And the next one, as you can see over here, if you look at the first figure over there, it has an excellent production. Efficiency is very good. On the other one also, it has a very good stability as well. And one of the reasons for that is the surface area is very high. So basically, we have a very high surface area. We have a higher contact, and therefore we have higher productivity, higher efficiency. But also the stability is also high as well. And so we moved into, now the first one is in between. The second one gave us a very good idea on where we should head to, and results were extremely promising. And that's why we moved to something even bigger. And this is a patent that we have submitted last year. And you can see, if we compare it to platinum with carbon, the red dots over there, you will see that our catalyst is even much better than that. It has more than 30% higher efficiency than the current commercial one. And what we have done is, now we are continuing with that. And recently, last week, we got another fund for that from His Majesty Trust Fund, working on the development of this patent into a commercial product, inshallah ta'ala. So moving on to more of those, and as you can see again, It has a very high stability. This is working at more than 140 hours of production. Very high stability in neutral conditions, but also acidic and basic. And what this gives us is we can use this both for the membranes in both anodes and cathodes, but also in the bipolar layers. So it can be used for the whole process, not only in one as the others. And this is where we move to CO2. So if Oman is interested in hydrogen production because it wants to be a leader in green hydrogen production for environmental reasons, this is even more important because of course, we signed the Paris Agreement. We know that we have the net zero target is by 2050 in Oman. And so this is extremely important. There is no running away from it. And so what we are nanotechnologies engineers and scientists. So we don't look at what kind of think here. Okay. See, I didn't even put it. How we can use of CO2, whether it's in transportation or whatever. So what we have is, if we have CO2, for us, we don't think about storing it, natural storage underground. We think about utilizing it, converting it into added value products, whether it's methanol, ethanol, whatever utilization that is. And again, I don't know about the timeline. And so what we've done again, we began with a project where we do this kind of treatment, CO2 conversion, but also water treatment. But when we began, the idea was we do a new kind of water treatment followed by CO2. CO2, well, the treatment itself will lead to the removal of CO2. And what we realized is we can actually combine both. So what we have done here is, instead of having a treatment of the removal of organic matter and then producing of hydrogen, we can combine them both together. So what we have done is we've done different kind of organic. This study is for urea as part of wastewater. And what this does is, it's the same concept of hydrogen production, green hydrogen production, but instead of producing on one side, we produce hydrogen, on the other side, we produce oxygen. What we do is, on one side, we still have the hydrogen production, but on the other side, we are actually treating the urea. We are converting the urea. So we don't have the hydrogen evolution side and the oxygen evolution, we have the urea evolution. And so at the same side, at the same time, we are producing hydrogen on one electrode, but we are also degrading the urea and of course the other kind of materials. And again, as you can see, the results are very promising. And that is with respect to inorganic. This is an organic system, histidine with copper. Probably we'll skip all of that. And this is one of the latest projects. We began with this last year, which is the conversion of CO2, again, not in the usual methane and these kind of products, but actually into polymers. So we know that CO2 conversion, it's either with respect to photochemical, electrochemical, or thermochemical process. Now, we have a very big experience with photochemical, but not for CO2 conversion, but for water treatment. And we know the challenges that we have with that, with photocatalysis. And so what we looked at is said, let's move to thermal and electrochemical, because that is, there is more to it there. It's more promising compared to photocatalysis. And Again, the idea, as you can see, this is very similar to hydrogen, right? It's just a cell, a normal cell with the electrodes and cathodes. And so what we are looking at is, if we are going to make these catalysts, then it doesn't make sense that we get, again, just like for green hydrogen, expensive catalysts and utilize it, because anything expensive will add up and the whole process is going to be expensive. So in this study, what we do is we are using carbon, and we are talking about natural carbon. We make the catalyst out of natural resources from Oman. We dope it with nanomaterials to activate it, and then we utilize it for the CO2 conversion. And here are some of the results. As you can tell over there, and I don't know, these are very, very small, but the main production was acetaldehyde that we have produced from CO2 conversion. And this is what I meant by the last project that we have done, which is the CO2 conversion into polycarbonates. Now, polycarbonates are used everywhere. Wherever you go, you will see polycarbonates, whether it's on your phones or it's in bottled water or anywhere else. And so the idea is we use this CO2, we capture the CO2, and we use it for polycarbonate production. Because one of the reasons why we have a problem with polycarbonates is it uses phosphagens, and phosphagens is extremely dangerous. It's not only expensive, but it's also extremely dangerous. And so what we have done is, let's look at a better, more environmentally friendly process, but also, of course, we need it to be less costly as well, because environmentally friendly will not cut it if you are going to go into the industry. And what we were looking for is either COFs or MOFs, metal organic frameworks. That is because it has a very high selectivity. You can manipulate it to provide you with whatever you need. And so we actually have a very good previous result that we have, and we are currently continuing on this with really very good results. What we only need is we continue on this path to make it even better. And this is here only to show you that we recently returned back to solar cells, dye-sensitized solar cells. We left this in 2021. However, where is Dr. Siko, Kondaya Siko? I don't see him. Basically, we have this kind of collaborative work with Dr. Kondaya from Utah Shinas here. This is one only of many work that we have done. We have been visiting each other for many times in the past 3 years, working on this. And this work is, of course, the work of Dr. Kondaya with his team in here. And just to show you that really with collaboration you can do a lot of great work. Now what we have done before is something different. We looked at the colorants, the dye, and we fabricated a lot of dyes to make sure that these are very good in the solar cells. More than 40 dyes we synthesized. Unfortunately, we have very good ones. Unfortunately, the stability was not there. So we could not make it work for a long period of time. Now, this is a little bit different, using natural resources to see if we can have a higher production. And the work, again, is quite promising. Hopefully, we can make it even better in the future. And basically, what I would like to say with that is, really, if you are very interested and you are committed to research, you cannot be committed to research without collaboration and industrial involvement. And this collaboration can be national or it can be international. But believe me, it's extremely important. What we have is we have very strong collaboration nationally almost all the universities, probably not all, but also we have high international collaboration as well with more than 22 countries all over the world. And this basically makes our work also easier because we divide the work between us. We are not experts in all the steps of the process. We are experts and we are very good in a few parts, and we know that there are teams that are extremely good on the other parts, and we complete the work together, each one of them having all of that. And we still have this kind of collaboration with these entities. Of course, also we cannot really say that we can succeed without the industrial partnership, and we have very good funding from different industries. We have projects funds from OQ, from PDO. The last one we got was from Membrane, from OIA with NEMA. Currently we have 2 projects from NEMA. We have 3 projects from OQ. We did 2 projects with PDO, and hopefully we can manage other projects as well. Now, we are still beginning with all of this. Yes, we have very high experience, we have done a lot of work, but we are still in the beginning stage. We still have a lot of things to do. And hopefully we can manage in the coming years, we can manage to continue this work, make it better, see what kind of new technologies that we can develop to make all of this better, more efficient and less costly. And with this, I would like to end my talk. Thank you very much.
As we move forward, it is fitting to take a moment to recognize and appreciate the individuals and organizations whose support has made this symposium possible. We now move to the ceremony of recognition, a moment to extend our heartfelt gratitude to the individuals and organizations who have contributed immensely to the success of the symposium. I would like to invite Chief Guest Dr. Hamdan Al-Fizari, Dr. Ahmed Al-Balushi, Assistant Vice Chancellor, Newtas Shinas, Dr. Moza Al-Shahi, Deputy Assistant Vice Chancellor for Academic Affairs in Newtas Shinas, and Mr. Huda Saadi, the Head of Engineering Department, to the stage to present tokens of appreciation. Starting with our distinguished keynote speaker and moderator, Dr. Mohammed Al-Abri. Please come on stage. Next, our sponsoring company, Suhar Aluminium. Next, we have the moderators, starting with Dr. Ramakrishna Bita, Dr. Venkadishan, Dr. Abdul Hamid Khalifullah, Dr. Mushtaq Hussain, Dr. Ghulam Dastagir Khan, Dr. Sanjay Gupta, Dr. Balavi, Dr. Joseph Santhapan, Dr. Lenny Anslim, Dr. Lenin, okay, Dr. Mahmoud Yunus, Dr. Inder Pal Singh, Dr. Nader Ali Abdullah Shibli, Dr. Rajalingam, Now, moving to the evaluators, Mr. Walid Saeed Ahmed Al-Khwazimi, Mr. Rabia Ahmed Saeed Al-Saadi, Mr. Yusuf Al-Saadi, Dr. Wadha Muwafaq Tawfiq, Mr. Abdul Basit Muhammad, Mr. Mahesh Chandra, Mr. Abdul Basit Muhammad, then the scientific publication partner IEEE. Now, we would like to invite Dr. Ahmed Al-Belushi, Assistant Vice Chancellor at UTAS Shinas, to present the memento to our chief guest, Dr. Hamdan Al-Fizari, appreciating his presence and continued support for the symposium. We now transition into the heart of the symposium. Chief guests and dignitaries are invited to open the students' poster exhibition in the main building lobby, and all other audience are expected to be seated in this venue for the upcoming keynote speech too. Evaluators of poster presentation are requested to proceed with the poster evaluations in the main building lobby.
Again, the rule for poster presentation student, you have to go there. Moderator, sit here. Poster evaluator, go there. Again.
The students with poster exhibition, please proceed to the main building. And the audiences and the moderators, please remain seated in the venue. Moderators, please remain seated in the venue, while the students with the poster exhibition, please, you can proceed to the main lobby. Say it again.
بس يبن عبد الله يكون عند مستر يوسف لسه عشان يعرف
We now move to the second keynote speech. It is our pleasure to welcome Dr. Naga Raju Goli, Research Assistant Professor.
Yeah, I don't see a way. Yeah, can you just check with your camera and doesn't? Yeah, we can. Yeah, we can see this, right?
I can't see there.
Okay. What about presentation, sir?
Yeah, it's there.
Can you just check with your presentation?
Yeah, it can be presented, sir.
Yeah, it's coming. It's coming. Yeah, presentation was coming. Yeah. Okay. 1 second.
Okay. We now move to the second keynote speech. It is our pleasure to welcome Dr. Naga Raju Goli, Research Assistant Professor from the Department of Material at Imperial College London, who will be joining us virtually to share his valuable insights on additive manufacturing of microbatteries for wearable sensors. You can start, sir.
Nagaras, hello? Nagaras, can you hear me?
Hello, sir. Hello.
Nagaras, you can share your PPT.
You can start your presentation.
You can start your presentation, Dr. Nagaras.
Just you can share your screen and you can start your presentation. Thank you.
Is the mic is enabled or what? Voice is coming. His voice is coming.
Can you see my screen?
Yes, yes.
Yes, I can see your screen. Yeah, thank you. Good morning, everyone. My name is Nagaraj Goli. I'm working as a research assistant professor at Imperial College London. So thanks for Dr. Professor Kondareddy sir for inviting me for this nice presentation at Shinhas University. So today I'm going to talk about my research that I'm doing at Imperial College London on additive manufacturing of microbatteries for wearable sensors. So before that, I'd like to briefly introduce myself. So I have graduated master's degree from Nagaraj University. So my supervisor, Dr. Kondareddy sir, is currently working there. So he taught me the chemistry in MSc. So then I went to Kingsley University for my PhD studies. So my research area is on electrochemistry. So where I used to develop the energy storage devices. And then I did 2 years postdoc in the same university on lithium-ion batteries. Then I moved to Ireland, Trinity College Dublin as a research fellow. So where I developed high mass loading anode cathode materials for lithium and sodium-ion batteries. Currently, I'm a research assistant professor at Imperial College London from 2022 September. So I'm currently working on 3D printed microbatteries for wearable sensors. So I have several academic awards and research scholarship during this tenure. So I'll also briefly summarize my research experience here. So as I told you, like I started working doing my PhD on lithium-ion batteries, where I used to develop the transition metal oxides and carbon-based composites for as an anode for lithium-ion batteries. These anodes were stored stable capacity for long-term cycling. Around 800, there is no capacity fading. These kind of anode materials have been developed during my PhD. Then I also started working on sodium-ion batteries, especially using the solar light and to enhance the capacity of the battery. So when the battery is under dark, the capacity is minimal. When we eliminate the battery under light, the capacity has been enhanced. So because we use the TMDs, transition metal dichalcosinides, are the light absorbers that absorb the light and accelerate the charge storage process. That's why when the battery was eliminated in the light, the capacity has been enhanced. So these kind of materials currently we are investigating here. So these batteries were studied using the inoperando and ex situ characterizations, and we are currently investigating the fuel cells for commercial electric vehicles. So the printed batteries have attracted significant attention for wearable sensors. So we started printing 3D printed aqueous batteries with high mass loading and high porosity for wearable sensors. So previously I used to work on fiber-based wearable supercapacitors using the simple and scalable methods. So I used to grow transition metal oxides, layer double hydroxide, transition metal sulfide based materials, and these hybrid supercapacitors achieved high energy density and power density.
Facing some technical issue. Where is Abdul Bashi? Sir, where is Abdul Bashi? Abdul Bashi? In his laptop? No, here nothing there. No, it is open, sir. Hello, Nagaras? Where is Abdullah?
Yes, that you can listen to, so that you can talk to him, right?
Nagaras, can you hear me? Hello, Nagaras? Hello, Nagaras, can you hear me? Hello, Nagaras, can you hear me? Problem inside or outside?
Hello, Mr. Gori. Can you unmute your microphone, please?
Hello. Can someone please respond to me? Can I start?
Yes, please. Nagaras, okay,
Thank
start.
you.
Yes, go ahead. Go
Thank you,
ahead.
sir. Okay, can I start from first, sir?
Yes. You can go after.
Yes, go ahead. Go ahead. You can continue now.
Good morning, everyone. My name is Nagaraj Goli. I'm a research assistant professor at Imperial College London. Thank you, Professor Kondaredu sir, for inviting me for this talk. So today I'm going to talk about my research at Imperial College London that I am doing. So it is based on additive manufacturing of micro batteries for wearable sensors. So I did my PhD after a PhD from Korea and my master's degree from Nagarjuna University. And then I did a postdoc and research at University College Dublin, that is called Trinity College Dublin, where I started working on lithium and sodium ion batteries. Then I moved to Imperial College London as a research assistant college, I am also working on several projects on aqueous batteries that are printed by additive manufacturing technology. So using this technology, we can print anodes and cathodes with high mass loading, and we can also increase the capacity because the mass loading is very high and the surface area of these electrodes also very high. So that is the advantage of the 3D printing over the conventional electrode designs. So at Korea, where I did my PhD, I used to develop the fiber-based wearable supercapacitors. So these fiber-based electrodes were designed using the binder-free technology by integrating the transition metal oxides, layered double hydroxides, transition metal sulfides as an wearable electrodes, and then these fabricated hybrid supercapacitors achieved high energy density. So these works were published in top-tier journals like Advanced Energy Materials, Nanoletters, ACS Nano, Journal of Power Sources. So these are the top-tier journals which I published. So why do we need energy storage? So we know that the global warming and pollution is increasing every year. So we need to mitigate these pollution issues by using energy storage devices or energy conversion devices. Especially these energy storage devices, they convert the chemical energy into electrical energy. So using such devices, we can mitigate the use of fossil fuels. So thereby we can suppress the pollution issues. So especially the energy storage devices we are currently using in the electronic devices like mobile phones, laptops, cameras, etc. Nowadays, these energy storage devices started using in electric vehicles. So the ongoing research is also establishing towards the grid scale applications by using these energy storage devices. So there are various kinds of energy storage devices are available based on their energy density and power density. Especially the lithium-based energy storage devices shows much higher energy density and power density. However, they have several issues. So in terms of safety that I will be explaining in my later slide. So the zinc-based energy storage devices have been attracted as a future technology towards sustainable energy storage devices because these zinc-based energy storage devices are highly safe and they doesn't get any flammable issues. So why we are using lithium-ion batteries in these electric vehicles? Because these batteries are the best energy storage devices in terms of energy density. So the charge storage mechanism in these lithium-ion batteries are based on the intercalation and deintercalation of lithium ions from the cathode to the anode. So that's why the charge transfer takes place from one electrode to the another electrode. As a result, these lithium-ion batteries shows high voltage, nearly 3 to 4.5 volts. Because of this such high voltage, these lithium-ion batteries generally shows high energy density and power density. So because of these interesting advantages, properties, they started using in the automobiles and portable electronic devices. However, some issues there in lithium batteries, as I told you, like safety issues, and we are also aware of that. When the battery temperature gets high, there is a fire issues might happen at the cell, and also the electrolytes that use in the lithium batteries are harmful organic-based electrolytes. And limited availability of materials and high cost is also another issue for these lithium batteries for scalability or low cost electric vehicle applications. like a layer by layer approach, so we can print the number of layers based on our ink yield stress. So if our ink having good rheological properties, we can build the number of layers one by one on the electrode surface. So thereby we can increase the surface area. As a result, we can improve the energy density. Usually, for making the battery electrodes, we use the conventional thin film casting method, like here as shown in this photograph. So using this technology, the mass loading will be limited to less than 2 milligram per centimeter square. So as a result, these thin film electrodes achieve lower capacity. So in order to get the desirable capacity, we need to stack the number of cells together. So like more than 5 cells, then only we can get the desirable capacity, because the mass loading of the material is limited. If we increase the mass loading to more than 40 milligram per centimeter square, we could able to achieve the capacity and energy density, and we can downsize the stacking layers of the cell. However, if we increase the mass loading on the electrode surface, there will be a sluggish ion transport inside the thick electrodes. So even we don't have porosity in the electrode surface, the ion penetration or electrolyte penetration will be minimal. As a result, ion kinetics will be lower and we can achieve only lower performance. Moreover, when we make thick electrodes, there is a possibility of cracking on the electrode surface, like delamination, weak strength, and poor rate performance. So because of these issues, so making thick electrodes is a challenging task. That's why recently several approaches started using the 3D electrodes by using the templates like polystyrene. So then they grow the anode and cathode materials on these electrodes so that we can increase the surface area, we can increase the mass loading, and eventually we can increase the capacity. However, using these template-based methods to make the 3D electrodes, we cannot make 3D electrodes with different geometry. So the freedom of geometry will be minimal, and we cannot miniaturize the electrodes into tiny shapes, tiny batteries. Also, it is difficult to achieve this. So using the 3D printing technology, so we can print the electrodes into small scale. We have a freedom of geometry, and the surface area and mass loading also will be increased. As a result, the fast transport kinetics and lower strain in the battery will be resulted. So when we make the 3D printing, so we need to make ink formulation. So we must need a polymeric ink along with our battery materials. So some people, they started using the graphene oxide as additives, and some started using the capillary suspensions to make the highly viscous inks. So as I said, binders are typically needed to make battery material inks. So majorly the polyvinyl difluoride as a commercially available polymer was started using. So using this PVDF, we need to use solvents like N-methylpyrrolidine, which is a toxic solvent. So this PVDF is only dissolvable in this solvent. Moreover, using these high amounts of PVDF, the electrode will not be having high conductivity, and moreover, these kind of formulations are not eco-friendly. So we need to use water-based sustainable binders that are low cost. So these binders can be soluble in water, and they are highly adhesive with environmental friendly features. So this is the cellulose polyvinyl pyridone, which is one of the organic molecule, but it is able to dissolve in water. And hydrogen is a biopolymer, so this is also can be dissolved in water. So we investigated these kind of sustainable polymers to make the battery inks. So whenever we do inks for 3D printing, we need to make inks that follows three important features. One is the yield stress. So yield stress is nothing but the ink should be not flow when we are not extruding. So for example, if we incline the ink slanted direction, it should not flow down. So this is that property. However, when we started applying the pressure, the ink should started continuously flowing. through the nozzle. So if it is clogged or if it is doesn't have like a running kind of behavior, the number of layers will not be stacked one by one. Shear thinning behavior is another important parameters. As I told you, when we extruded the ink from the nozzle, it should continuously flow without any clogging. Another important feature is the structural recovery. So whenever we print the one layer, it should be stable and it should not collapse easily. So because we need to print number of layers stacking one by one, so these properties should be studied through the radiological measurements, especially by using these three important features. So as I mentioned, like in my first work, I used cellulose as a water-based binder to make 3D printed graphene carbon nanotube cathode. So the cellulose was dispersed with the graphene and carbon nanotube suspensions to make different layers of the 3D printed cathodes. So these 3D printed cathodes with the number of layers around 12 shows 50 milligram per centimeter square with high porosity. So the morphology we can see here, the wood pile structure graphene shows high porosity and the conductivity will be enhanced by having carbon nanotubes over the graphene platelets. So the conductivity with the graphene carbon nanotube after eliminating the cellulose shows much higher conductivity than the graphene or graphene carbon nanotube before annealing the electrode. So the ink also shows shear thinning behavior and having high storage modulus for good printing. So I also did some electrolyte modification in the cell. So this is the pouch cell which I made using the 3D printed graphene as a cathode, zinc metal as an anode. So the electrolyte will be conventionally uses zinc sulfate, but I use the hybrid electrolyte where I mix sodium chloride as an additive to the zinc sulfate electrolyte, and then I suppress the dendritic tissues on the zinc anode side here. The green line shows the zinc plating stripping curves of the zinc ion cell, whereas with the zinc sulfate and electrolyte, the dendrites started growing after 70 hours of the plating. So when I add the sodium chloride, the dendrites were minimized and the cycling stability has been extended to 450 hours. So this is the XRD which shows that the zinc hydroxy sulfates were grown when the zinc sulfate was used. When we use the sodium chloride additive, there were no zinc hydroxy sulfate dendritic byproducts on the zinc metal surface. Visually also we can see here the sodium chloride electrolyte surface, the zinc metal surface doesn't have any dendritics, whereas the zinc sulfate based electrolyte having the dendritics on the zinc metal surface. So the cycling stability of the cell has been extended, is seen here. We can see the hybrid electrolyte based cell shows much higher capacity, whereas the zinc sulfate based cell died after 1200 cycles. So the capacity versus number of layers also was studied here. By increasing the number of layers, the capacity has been expanded. However, there is a threshold between the 8 and 12 layers because there is no much capacity improvement beyond this number of layers. So these printed zinc ion capacitor also showed good rate capability upon increasing the current density, and it recovered very well after reaching to their initial discharge current. Also, at Imperial, we were printing the 3D printed zinc ion batteries using the fully printed zinc anode and fully printed cathode and fully printed electrolyte. So this is the zinc anode that we printed, which is based on the zinc and the graphene. So the graphene protects the zinc from the dendritic growth. Moreover, there is a surface area enhancement through the pores that we printed into the wood pile. So this zinc anode could be expected to show good cycling stability without dendritics. So the 3D printed manganese oxide was also carried out because we need to make the battery into miniature scale. So followed by the electrolyte with good conductivity was also printed in the form of zigzag patterns. Initially, the anode stability was tested in comparison with the bare zinc. So the black line shows the bare zinc, whereas the blue line shows the 3D printed graphene zinc electrode. So we can see till 500 hours, the cell lasted well with lower voltage crystallities. That means that the graphene reduced the nucleation barriers by suppressing the dendrites, and it enabled the faster deposition kinetics of the zinc 2 plus ions. And we can also visualize that the stable voltage hysteresis loop is presented. This is a good combination to enable the cycling stability of the zinc based micro batteries. So we using that zinc anode, we made a interdistated micro battery. So these interdistated micro battery having a manganese oxide based cathode and zinc based anode, followed by the electrolyte printing in between these two electrodes to make a fully full cell of zinc ion battery. So the encapsulated ion battery, zinc ion battery, can be usable for portable electronics, even for the Bluetooth proximity sensors. And we can see the stability here. The peak currents were almost similar upon increasing the cycle number. We can also compare the capacity of our battery with the commercial batteries that is available in the market. So we can see that our device shows much good rate capability than the commercial cells. The commercial cells are non-rechargeable, so we have to use at once and we have to throw them after using. But whereas this printed battery can be used several times, so we investigated the capacity upon increasing the current density. So which means that this battery shows good rate capability. So having the high capacity and high voltage window, we then used two cells together in a series to use them to power the Bluetooth sensor for a long time. So in summary, I would like to conclude my presentation with the development that I have been done so far in the 3D printing technology. Especially we use the water-based binders, water-based sustainable binders to print 3D printed electrodes. So the ink showed the high viscosity, and using that high viscosity, we can able to print multi-layer 3D printed electrodes with high pores and high surface area. So the printed devices achieves high electrochemical performance because of the high surface area and high capacity. And using these 3D printed batteries, we can power up the portable electronics like sensors and wearable devices. I'd like to thank my group for helping me to carry out this research. Especially, I would like to thank my supervisor, Cecilia Matevi, and I'd like to thank my group members for the collaborative environment in the group. And thank you for your attention. So if you would like to ask me any questions, feel free to ask me. Thank you very much.
Yeah, thank you very much for your presentation. Any questions? Any questions?
Hello, Dr. Naras. Hello?
Sir.
Naras, can you hear me?
Yeah, I can hear you, sir.
Thank you for your valuable presentation. Here, I have a small doubt here.
Yes, sir.
Hybrid systems during the conversion of electrical energy, any fluctuation is there? There is no any fluctuation issues during the fabrication of this type of electrodes?
You mean the battery cell or like a half cell cell?
Yes, half cells.
So this is the half cell which we
Yes.
made.
Yes.
So actually the zinc metal batteries, we need to make half cells. That means that we have to take both zincs together.
Yes.
Zinc versus zinc.
Yes.
And then we can see that there is a little slight fluctuations were there. This might be happened because of the weather changes. If we maintain the room temperature in the cell, we could able to make the capacity or voltage variations without any fluctuations like this. As we know, the UK having like a harsh weather, especially in the winter.
Yes.
So there is slight variations in the voltage hysteresis too. But if we test these cells in the oven at the optimized temperatures like room temperature, we can mitigate these kind of fluctuations.
Okay, thank you. Sir, any doubt? Ask to.
Thank you very much.
Thank you, Nagaraj. 1 minute. Please, please.
Thank you so much for your informative speech and your valuable time about the microbatteries, sir.
Thank you very much.
Thanks, Dr. Nagaraj. Thank you so much for your valuable information.
May I leave then, sir? Is there any comments?
No. Only from my side, they are very happy. Thank you for your valuable speech on micro batteries and sensors. Okay. Thank you so much for your contribution for this national symposium. Thank you so much.
Thank you very much, sir.
Yes, welcome. Please convey my regards to your family.
Thank you, sir. Thank you very much.
Welcome.
What type of a learning the student, what type of a learning the student is, a student can be, I mean to say that, like, a student is eligible, a student likes to learn what type of methodology, what way the student has to be, like we have to follow the training for the student. So those things can be decided based on the classes. Smart learning environment. So here, if you see the diagram, so here there is actor and contents. Then there is the things also. IoT things will be used and pedagogy methods. In this, it includes the smart classroom, smart labs, smart library, smart simulation, smart evaluation, and smart security access. Security and access. These all things can be used in the smart learning environments. AI technologies used, like what all things we can use are used for the development of an environment. NLP for the communication, natural language processing for the communication, machine learning for the personalized recommendations, and predictive analysis for the performance. And a chatbot also can be integrated here to ask more and more questions if it is required in the class. Features of the smart education, adaptive content delivery based on the student needs, the content can be delivered. AI tutor and feedback agent can be used. Monitoring tools for the student progress. Definitely, this is the one of the important thing what I'm planning here. Monitoring tools for the student progress. So the AI can keep on monitor like how a student is learning, and based on the learning, so we can give some evaluation methods like conduct a kind of a test and whatever type of things which is required to understand that the student is learning properly or not. Based on that, the measurement tools or monitoring tools we can create along into the system. Smart education ecosystem. In the smart education ecosystem, it includes the smart learners, smart content, smart teachers, smart infrastructure, smart pedagogy, and smart assessment. All these include in the smart education ecosystem. Evaluation and findings. Surveys indicate high satisfaction, increased motivation and engagement, positive feedback from the both students and faculty. So these will be the future of the
these are the implementation methods which will be followed. Impact of education in Oman: aligned with the national goals, empower the students and educators, scalable across institutions and regions. Challenges and future work: data privacy and infrastructure concerns. So always the data privacy is the one of the concern. Like after the conducting the survey or after inputting all the data of the student collected, and so that will be the privacy of the data will be one of the concern. Plan to include AR VR to promote linguistic support. So this is also one of the challenge as I discussed before. Also the AR VR technology, virtual reality and augmented reality also can be included into this type of a system. So where the student can learn much better way in the understanding. Continual iteration and improvement. So that's also one of the challenges what currently we may face. Conclusion: AI transforms education, smart education enhance personalized learning outcomes, supports national development goals. And that's all from my side. So this is the AI and education concept. As I discussed, so there's a plan for developing this type of a system. So that's what the review is conducted, took thorough details, like have done different types of studies to understand what type of a system, what type of a platform can be generated for the students by using the AI. That's all from my side. Thank you so much.
Thank you, Dr. Suresh. I have just few questions. The first question is, what do you think are the limitations or the drawback if you use AI in education?
So the limitations can be different, like if the student is not answering the initial survey when it is done to understand the student, not in the while developing the system. So after the developing the system, so any student we are going to test we input the data of the student. So if the student is not answering correctly, like the way exactly it is required, so then the AI may give the wrong result also. That is the one of the drawback if the student is not answering, because it's based on the student response. If the student response is not correct, not accurate, so then we may run into the a wrong type of results. That's the one of the main drawback what I feel.
And do you think traditional teaching complements AI in education, or do you think AI is going to completely take over the traditional teaching?
No, sir, definitely not. The AI completely cannot take over the traditional teachings. Of course, there is a like as we say, the chalk and board method has to be there. So where we can add some kind of value added to our traditional education, which can give us in identifying the student ability to learn the methods and the classroom management for the different students, and we can also give the personalized feedback for the student or based on the learning. So there we can use along with the teacher, like if we have an AI for the support, so then definitely it can give the more better future for the students.
So, have you done any kind of an experiment in your class, or do you have any data to support what all you said over here about the advantages of AI?
Sir, actually, currently, again, I'm repeating, sorry. So we have one budding project here for the AI in education using the AR/VR. For that, we have created a survey and we have collected the partial data. I mean, the survey is not yet completed, so we have collected some data. So shortly, we are going to analyze the data, and based on that, we have already published a GP paper where we are only happy to put the AR/VR same way. So same kind of a method I'm planning for using with the AI, purely with AI, not including the AR/VR technology here. Since I have already have developed the questionnaire and all the things with the AR/VR technology, so similar type of things also I'm planning for AI in education.
Okay, Dr. Suresh, that's all from my side. Thank you very much.
Thank you so much, sir.
Thank you, Dr. Suresh. I think, unluckily, you are the third presenter also.
Yes.
So I think you have to take a break,
I'll
take
just
a
give
sip
me a
of
minute.
water. Yes, 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 please. need to drink something? Yeah. Yes, still or no?
Yes, sir, I'm finished, sir, because have a research presentation there in the college. I'm in the home currently.
Yes.
Basically,
All right.
still not in the office. Just I'm studying abroad in the office. Morning I tried, but we have a lot of problem
So
in the office.
if you are ready, just you can. Dr. Ghulam, are you ready for that? Yes.
Yes.
So you can
Yes,
go
sir.
ahead. All right. We are waiting for you.